to Atoms and Sporks, and in this video, I want to talk about some of the incredible technology we use to take a bunch of atoms and cool them to only the teeny tiniest fraction of a degree above absolute zero using nothing but light. However, before we get into that up front, I think a very natural question people have when they hear about stuff like this, how physicists have forced such and such to some stupid, absurd low temperature, is the simple question of why? Why do we want to do that? Is it just to show off? Well, sometimes it is, to be honest, but really, no. It's for three main reasons. The first reason is because physicists are in the business of exploring and describing or modeling all that nature is capable of. And especially with the advent of quantum physics, it's become very clear that nature can do some very different, some very incredible things at very cold temperatures. And we'd like to explore and understand and maybe even technologically exploit those things. The second reason is actually because even if we are actually aiming to study properties of atoms in everyday, regular situations, not at these obscene temperatures, we still need to know precise information about things like the energy levels of those atoms. But at finite temperatures, actually measuring these levels can be difficult. And that's because if you have a bunch of atoms at a finite temperature, these energy levels actually get blurred and imprecise. We'll actually come to understand a big reason for this later on, but the simple fact is, this is a big issue if you want information about energy levels that are very close to each other in energy. So to measure those quantities, you have to cool the atoms down. And that actually leads nicely into the third reason, which is for technological applications. And that's because one technology where we use such ultra-cold atoms is in atomic clocks, which basically keep time by cycling between these energy states. If those energy states are broadened or blurred, the clock is less accurate. And these atomic clocks are essential, for example, for things like GPS technology. Another cutting-edge field where so-called ultra-cold atoms are important is quantum computing, where precise control and manipulation of quantum states is a must. They're also key in the related field of quantum simulators, where one teases insights into one system by directly manipulating a different system. The idea being that if you know that the two very different systems actually have a deep mathematical connection in their physical behavior, you can learn a lot about a difficult to study system by exploring an easy to control and measure system. Ultra-cold atoms are great for these kinds of quantum simulations. So those are generally our reasons. Either we're trying to explore what nature can do in new regimes, or we're trying to get more accurate measurements of things nature does at more regular regimes, or we just want to make new technology. But okay, that's the why, but then how do we do it? Well, there is actually a lot of ways, and the point of this video is really just to scratch the surface and to introduce some of the key ideas. One of these key ideas is that light can directly exert forces on individual atoms. It can push on them, and it can do that because it has momentum. If you're unfamiliar with this, I've already actually done a whole video on it, so you can learn more there if you're curious. But given that light has momentum, then if I have, say, a beam of atoms heading to the right, and I have a laser beam shining to the left, well, if those atoms absorb that light, they are then pushed to the left and thus are slowed down. And to cool something, that's what we want to do. We want to slow the atoms down. Temperature is basically the average speed of an ensemble of atoms. Though keep in mind that in such a thermal system of atoms, they will have a distribution of speed. Some will be going faster, some slower, and all of their directions will be totally random. But in a nutshell, the average speed is basically the temperature. And so to cool atoms is to slow them. However, unfortunately, it's not nearly as simple as just shining any old laser at any old atoms to get a cooling effect, if only. And that's due to a few key bits of physics that we really need to understand before I can introduce the various techniques. So bear with me while we touch on some of the key fundamentals. The first is that a given type of atom will only absorb light of a certain, fairly precise set of frequencies called atomic resonances. In a nutshell, the reason for this is because an atom can only absorb light if it can use the energy of that light to transition from one state to an excited higher energy state. And due to quantum physics, the energies of these sorts of transitions are generally discrete, meaning it's kind of like Goldilocks. If the frequency of light is too high or too low relative to one of these resonances, the atom won't absorb its energy because it has nowhere to put it. The second potential issue here is atomic re-emission. If an atom absorbs some resonant light, it is pushed by it, and its momentum is changed. That's what we want. However, as we said, the energy of that light has gone into changing the states of the atom from one energy state to a higher excited energy state. However, the thing with excited states in quantum mechanics is that they are not stable. After a certain amount of time, based on what's called the excited state lifetime, the atom will give back that energy by re-emitting new light and fall back to its ground state. So at first glance, it might seem that this whole idea cannot work. An atom absorbs light and as a result gets a little push, but then it re-emits that light a bit later and is recoiled or pushed back by that emission. So the net push would seem to be zero with nothing really being accomplished. But actually, that's not the case. That would be the case if the atom was absorbing light from all directions. But when an atom re-emits the light, it does so isotropically, or omnidirectionally. In other words, it emits in all directions equally. So that's maybe a little subtle, but the point is, in our little setup, absorption is only happening in one direction, but re-emission is happening in all directions. So absorption does indeed result in a net push, but re-emission doesn't, and that doesn't undo things. Finally, the last bit of stickiness we have to understand is what is called the Doppler effect. The Doppler effect is what is happening when you hear a police or ambulance siren, and as the car is heading towards you, the siren sounds higher pitched. But after it passes you and starts speeding away from you, its pitch then shifts to a lower frequency. That's the Doppler effect. This is a general phenomenon that happens with all wavy things, including light, where basically, if I have a source of waves emitting with a certain frequency, the frequency you receive as a receiver of those waves will be upshifted if you have a velocity towards the source, or downshifted if you have a velocity away from it. Now, let's think about what this means for our atoms and a laser. Let's say I have a laser that outputs green light. By saying it's green, I'm saying it has a certain frequency. And let's say I have an atom that has an atomic resonance corresponding to red light. Well, if the atom is stationary, it won't absorb the laser. It's too high frequency. However, what if the same atom was moving away from the laser? Well, because of the Doppler shift, it now receives that light as a lower frequency. We say it is redshifted. Well, now it actually can absorb the light, and it does. This, by the way, is also one of the main reasons for this broadening of energy levels that high temperature causes that we talked about previously. A gas of hot atoms, as we discussed, has a distribution of speed and direction. So if I shine a laser that is off resonance for a stationary atom, there may still be atoms in the gas that see it appropriately red or blue shifted, such that for them it is resonant and they absorb it. We call this Doppler broadening. But okay, enough with the fundamentals. Our key concepts were that light can push atoms if the atoms can absorb that light, that atoms can only absorb certain frequencies, and that the frequency of light an atom sees in terms of whether it can absorb or not actually depends on its own motion relative to the laser source. So with that understanding, let's finally get on with our main discussion. How do we actually cool atoms down? Well, historically, the first starting place was by trying to cool atomic beams. Now, the term atomic beam probably sounds both like we're accelerating atoms to make them go really, really fast, which, is the opposite of our goal, and also probably sounds like a super fancy device like some enormous particle accelerator or something, but actually no, on both accounts. To make an atomic beam, one basically just takes a gas in a box and just pokes a hole in the side, like popping a hole in a tire. Now, why would we choose to cool these beams rather than just a gas? Well, because as we said, if the light is heading in the opposite direction to an atom, and that atom absorbs it, the atom is slowed. However, in a gas of atoms, some atoms are heading towards the source, but others are heading away from it. And if an atom moving away from the source absorbs light, then it's actually accelerated by it. It gets a kick in the pants and goes faster, which is the opposite of what we want to do. So, given that, atomic beams are a simple and easy solution. And that's why, historically, this was the first step we took towards cooling with light. Pioneered by people like William D. Phillips, who won a Nobel Prize for this work in 1997, and Arthur Ashkin, who we've actually already talked about him and his 2018 Nobel Prize in an earlier video. And it works, a little bit. If you have an atomic beam whose atoms have a distribution like this, with a certain average speed or temperature, after the beam is done with it, it'll look something like this. And this distribution has, on average, a slower speed. The atoms are cooler. But looking at this, you can maybe see the problem. Only the atoms in a certain narrow range of velocities are being cooled down. And the reason for this is because of the Doppler effect. We said we'd pick the frequency of the laser to match a certain atomic resonance, but that resonance gets Doppler shifted by the motion of the atoms. And so if it was resonant when they were going fast, as they slow, they see the light as red shifted, and then it's no longer resonant. And that is what we're seeing here. So how do we stop that? Well, people came up with two very clever ways of attacking the problem. To reiterate, the issue we have is that as the atoms beam out and absorb the incoming light and are slowed down, their resonance and the light's frequency are Doppler shifted such that they then become off-resonant. So the two clever ways is to, in real time, as the atoms are flying across the experimental apparatus, somehow either shift the frequency of the laser or somehow shift the resonances of the atoms. One or the other is altered in real time to keep the resonance going in step with the Doppler shifting. The first of these approaches is called chirp cooling. We've seen this word chirp in a previous video about the 2018 Nobel Prize, and it just means a wave whose frequency is actively changing in time. And that's what we want to do. As the atoms are slowed by absorption, we want to actively detune or chirp the frequency of the laser to restore resonant absorption. The second of these approaches is called Zeeman cooling. Well, actually, if you want to Google and learn more or something about this, it's actually more often called Zeeman slowing. At the heart of this Zeeman cooling is an important effect of quantum physics called the Zeeman effect. In a nutshell, it is a prediction of quantum mechanics that if I have an atom with certain energy levels and I place it in a magnetic field, there will be a shifting of these levels in energy. And in fact, the stronger the magnetic field, the stronger the shift. And this is just what we need. We want to actively shift the atoms' resonant energies in flight. So specifically what we do is we put the entire apparatus in a magnetic solenoid that generates a magnetic field. And we make it so that the strength of that magnetic field decreases along the length of the apparatus. Like literally as the physical distance from the atomic beam increases, we have magnets with less and less coiling, what's called a tapered solenoid. And that's basically the idea behind chirp and Zeeman cooling. Either you actively tune the laser or you actively tune the atomic resonances in flight. Of course, I'm making it all sound so simple, but in terms of real engineering and experimental design, this was a huge triumph and took nearly a decade of work. On the chirp side, making tunable lasers is a huge difficulty and something to this day we don't still have as a technology as good as we'd like, and even if you have good ones, they need to be able to sweep at a certain rate, a certain speed, in step with the Doppler shifting. And for the Zeeman cooling, the coiling of the magnet took an exhaustive amount of revision of design and materials. Honestly, you should hear William D. Phillips talking about his and Hal Metcalf's effort in building these things. Over the years, they went from a hand-wound design, cooled literally by just constantly throwing wet towels on the thing, to epoxy-coated wires wound by lathe, cooled by a coolant system that made use of a non-conducting fluorocarbon liquid. But with these easy-to-dream-up but hard-to-implement ideas, you could take a distribution of speeds like this and bring it to this. And by 1985, such approaches were cooling atomic beams down to temperatures of around 1/10 of 1 degree above absolute zero, and about 25 times colder than the original atomic beams. But things didn't stop there, because once you've gotten your atoms slowed down that much, there's actually an opportunity to trap them and cool them further through the final technique we're going to talk about today, which is Doppler cooling. The reason Doppler cooling is called that is because unlike the other techniques where the Doppler effect was our enemy, we're constantly fighting against it, in this technique we can finally make it work for us. To see how, forget about our typical setup of atomic beams and consider a gas of very cold atoms that have been pre-cooled by some other technique, and that is pinned between 6 lasers, 2 opposing lasers for each axis. Now, remember, we're talking about a gas now and not a beam, so the atoms aren't all moving in the same direction, and the direction of their motion is random. And the trick is that we take our lasers and get their frequency to one that is just below a resonance of the system. We so-called detune the laser to an off-resonant lower frequency. As a result of this, we'll see, because of the Doppler effect, not only will these atoms start cooling down, but they'll effectively be trapped in place. To see why, let's just think about one axis. So I have 2 opposing lasers, and in their center I have this gas of atoms, and they're detuned to a frequency lower than an atomic frequency for a stationary atom. Now, there's a distribution of speeds and directions of these atoms, but let's look at one moving to the right. Well, because he's moving to the right, it's moving away from the left-hand laser, and thus it sees it as red-shifted to an even lower frequency. And so it's even more detuned, and as a result, it'll never absorb it. And that's good. If it did, it'd get a shove in the back and would get a speed increase. However, what about the right-hand laser? Well, it's heading towards that laser, and as a result, it sees it as blue-shifted. And, bam, look, it's now on resonance and is absorbed, and the atom gets a kick back. Do you see how this is working? If it's stationary, it doesn't absorb, because the lasers are off resonance. If it's not stationary, the laser in the direction, shining in the direction of its motion, which could potentially give it an unwanted speed boost, is now pushed even more off resonance because of Doppler shift, where the laser shining opposing its motion is Doppler shifted into resonance, and it is pushed back to a lower speed. And voila, Doppler cooling. Using this method, you can get to temperatures of about a few hundred millionths of a degree, or about 250 times colder than the limits of Zeeman cooling. Furthermore, what makes Doppler cooling different from the others is that it is also a trap of atoms. This trapping is often called optical molasses, and that's because it's not really an atomic trap in the usual sense, where the atoms are being held by an attractive force, usually through some magnetic or electric field, towards the center of the trap. Rather, the atoms are trapped because their direction of motion is constantly being scrambled and their speed constantly stolen. They're not pulled, but anytime they try and get anywhere, they're randomly knocked in some new direction, and instead, thus, they are forced to perform a so-called random walk. And it is this random walking that is largely holding them in the center of the laser beam. Also, by the way, a bit of flavor, one of the big people to first demonstrate optical molasses was Stephen Chu, who, because of this work, shared the 1997 Nobel Prize with William D. Phillips, who we talked about earlier, as well as with Cloud Cohen-Tanuji, whose contributions we may talk about in a later video. Stephen Chu would later then become Secretary of Energy for the Obama administration. So the guy is a Nobel Prize-winning physicist and former U.S. cabinet member. I've done nothing with my life. Well, on that note, let's wrap things up. These techniques are not actually our current limit for cooling with light. There are so-called sub-Doppler techniques. In fact, Stephen Chu and his group themselves accidentally discovered sub-Doppler cooling while trying to originally demonstrate Doppler cooling. But maybe such techniques are better as a story for another time. So, in this video, we learned about how to use light to cool things down, about how light's momentum can be used to push a speeding atom and slow it, and about how the Doppler effect can work against such attempts. We also learned about how these issues can be addressed by either actively changing the frequency of the laser in flight, which is called trip cooling, or by actively modifying the resonances of the atoms using magnetic fields, which is called Zeeman slowing. And finally, we learned about how one can use multiple counter-propagating lasers that are detuned to a resonance to both trap and cool a gas of atoms, which we call Doppler cooling.